Hi, Ivan.
Hey there. How you doing?
I'm well, thank you. We can hear each other. That's great.
Your volume level is a little low, I think.
Okay. I can move the microphone closer. Does that help?
Yes.
Okay. Dave should be admitting others. I saw that Joanne and John Doty had joined. Hey, I wanted you to, I wanted to thank you for being here today. And looks like several of our science communicators can join. So that's going to be hopefully make for a good afternoon.
Thank you.
Let me open up the Google Hangouts here to see if Dave has any messages for me. So we should also be streaming live on YouTube today.
Okay.
So we may get people that are viewing our conversation that are not part of our Zoom chat, so to speak. But hopefully, all the technology.
I'm broken out.
Hey there, you're breaking out all over the place. Good to see you, John.
Hi, John.
We'll wait a couple minutes for others to join. John, how is your healing going? I know that you broke a limb here a couple months ago.
Well, I saw my surgeon last week and he said I was 6 months ahead of the healing schedule.
Well, you've always been a very ambitious person. Hey, there's Joanne.
Oh, hi everyone. We're breaking. Hi. Hello, Scott. Hello, Ivan. How are you, everybody?
Good. How are you, Joanne?
And we have a science guest down here.
Yeah, the science guest is just a placeholder to.
Scott Thompson's.
The science guest is just a placeholder for the YouTube stream that's happening on my desktop computer, which is in a different room. So it had to join the meeting. So there's a phantom member of our breakout room here that is responsible for the window that's being streamed to YouTube.
I'm looking at your background there, Scott. Oh, that's most interesting.
Well, yeah, that's a small fraction of all the books I have.
Well,
a small fraction of the
books. Whereas my background is actual books.
There's actual books there.
Yeah, many of my books are virtual these days. I have, of course, being
and the actual Phyllis.
Oh, hi, Phyllis.
Who are you?
Who am I? Uh-oh.
How are you?
Oh, I'm fine, thanks. So we're streaming live now on YouTube. Please consider that before you disrobe or do anything else that might be deemed not child friendly.
I'm gonna have a drink.
Okay. From a beaker, nonetheless. That's fantastic. That very scientific.
Halloween at Michael's.
Ah.
They have the flasks.
I love your background. That's from 2001, right?
Yes.
All right.
Keeps telling my internet connection is unstable. What about me is not unstable?
Yes. All right, I'm going to lift my laptop down where I can.
Uh-oh, he's disappeared.
I disappeared. I shouldn't have.
And then you came back. It was magic.
Oh, good. So I was going to have my laptop elevated so that it's where my camera is. it makes it easier, the line of sights when I'm looking at the camera versus the laptop. But I need to have my laptop accessible because Dave may be chatting some messages at me.
So we're 5 minutes into showtime.
Yep. Well, let's see. I can't fix that. Let's see. How am I going to fix that? I'm going to have to go upstairs and fix something really quick. Dave said that I misspelled the link to our Zoom meeting in the YouTube chat. So give me about 3 minutes. I'll be back after fixing that typo. You may talk science among yourselves, certainly.
So far are we today? I just lost my Zoom.
I can still see ya.
Yeah, but I can't see anybody. I wonder what I did. I'll go back. Aha! Ah, I pushed the wrong thingy. My icon was, and then well, you know, it's a computer.
I'm very fond of Marvin the Martian saying, "Oh,
Yes.
drat these computers. They're so naughty and so complex.
Yes.
I could pinch them."
Yes. I'm with him all the way. Let's see. I can do this.
I recently had occasion to, there was a 1980s band called No, I don't know if it was the band. I believe the band was called Telex. And that reminded me, when I was young, businesses would have a Telex number.
Yeah.
So I went and looked it up, and they were pretty interesting machines. They had a speed of about somewhere between 40 and 50 baud. And I guess the Telex network was actually something that the phone system offered as like a dedicated system. It wasn't running over regular phone lines.
Hello, Abby.
Hi, how's it going?
So far, so good.
Hi, Abby.
Hi, how are you?
Doing great, thanks. Hey, I should let you know today we're actually doing a live stream to YouTube.
Oh,
It's about 15 seconds delayed compared to the Zoom meeting, but my technical assistant and lovely husband, Dave, will be doing the moderating. And as people look at the YouTube, they have a link in the video that says, if you want to ask a question in real time, then go to this site and it'll pop them into our Zoom meeting. And then Dave will make sure their question is not about, you know, when are all you atheists going to kill yourselves or something crazy like that.
so so was he the one who told me to go to a breakout room when I signed in?
Yes,
Yeah.
that was Dave.
Got it.
Yeah, he
So-
threw me out too. I had to go to the breakout room, so here I am.
Yeah,
Here you are.
we all had to do a little timeout there, huh?
Right. Now I will in fact change my name here. Rename. Since Alan isn't here, that's all. I'll take Alan off for now. There.
Okay, and then I'm going to open up the chat window for Zoom, and I'm also opening up the chat window for Google in case Dave has any messages for me. And I think we're good to go. I'm not sure if Mike Albro is going to be joining us today or not, but we'll just get started. So I have a question right out of the gate, a biology question that came to mind as I was reading a book on biology recently.
Mm-hmm.
And it said that the difference between a lot of our simian relatives and humans is the number of chromosomes. And I recall reading in a Dawkins book that changing the number of chromosomes is something that happens not not horribly infrequently in evolution. And what came to mind is if you have an offspring where, let's say, 2 of the chromosomes are merged, like in humans compared to great apes, well, who can you mate with? If you've got 1 fewer chromosome, then can you mate with any of your fellow tribe members or whatever? So I don't understand how the change in the number of chromosomes can get incorporated into the evolutionary tree. Do you have any insight into that?
No, I don't really. As you said, we differ from, I think it's chimpanzees, by 1 pair of chromosomes. And when you look at ours, it's pretty clear that we have the last bunch of chromosomes basically merged so that 2 chromosomes, or I should say 2 pair of chromosomes, became 1 pair of chromosomes. But beyond that, that's not really within my realm of knowledge, so I can't help you there. Sorry.
That's great.
Any ideas, Joanne?
I might do some further research on that before our next meeting then. See,
Yeah.
People who watch this video, maybe I'll have an answer by the time we do our next video. Anybody else have any thoughts on that topic? No?
I'm happy with the chromosomes I have.
Well, our chimpanzee evolutionary relatives have more chromosomes than you do. So
Only 1.
well, that might, I don't know. Isn't more better? That's what I hear.
No. 23 is better than 24.
All right.
Bread wheat is this crazy, I think it's hexaploid thing with far more DNA than human beings. But in fact, it's a very fragile plant that needs to be cultivated. It doesn't survive in the wild.
Mm.
Mm-hmm.
More is not necessarily better.
Right.
That's true. I think tomatoes, I'm no expert in the field, but if something is tickling my memory to say that tomatoes have one of the largest genomes in terms of not necessarily chromosomes, but the number of genes that they have is just phenomenal compared to many other organisms.
And long before Levi Strauss, too.
Oh, genes.
I'm sorry.
Oh.
I'm sorry.
Yeah, I had to read for that one.
All groans, gratefully appreciated.
Yeah. So I've got a topic for the 2 physicists we have online today. There was a news story this week about a new black hole that was generated from a merger of 2 lower mass black holes, and there's been some hubbub that I've seen on the internet about the particular mass of the black hole that was generated. So, do either of you have any? Are you familiar with the news story, and do you have any insights into why it's interesting to have black holes of different masses?
Well, we know about the really massive ones. They're in the center of galaxies, and they're active, and they're making jets of stuff coming out and all that. Those are millions of solar masses. And then we know about the little ones that are like 10 solar masses that are the remnants of supernovae. And then you get up into the tens, and those turn out to have been the bread and butter for LIGO and Virgo. Those are the ones they see merging most commonly. They're kind of high up on the scale of mass relative to the black holes we've been able to study by other means.
What are LIGO and Virgo? Could you mention that real quick? LIGO
and Virgo are the gravitational wave observatories. LIGO is the one in the U.S. It's got there's an installation in the Pacific Northwest. There's installation in Louisiana. Virgo's in Italy. They are things that measure the distortion of space between objects suspended as pendulums at the ends of multi-kilometer long vacuum tunnels. When a gravitational wave, I should say, passes through these, it actually changes the amount of space that there is between, it distorts the space. So it changes the amount of space there is between these objects, which are being kept still as possible. And so that's how and then they measure the distance with laser interferometers, and that's how they can tell the gravitational wave has passed through. And the sources of these gravitational waves are binary mergers of stars, very compact sorts of stars, usually black holes, that are of multiple solar masses, and they spiral in, and as they spiral in, they radiate gravitational waves, and that's why they're spiraling in. They're losing energy to the gravitational waves. And the interferometers pick them up, and we see, we see these ripples in those measurements. Now, the interesting thing about this new pair is that it probes a mass regime that we hadn't seen before. We've been looking mainly with X-ray astronomy at black holes of 5, 10, something like that, solar masses in binaries with ordinary stars. And then we look at black holes that are millions of solar masses in the centers of galaxies. The intermediate, what we call the intermediate mass black holes, the 100 mass of solar mass or thousands of solar mass black holes, don't seem to happen in binaries, and they're too small to make conspicuous stuff like the conspicuous jets and that sort of thing, like the multi-million solar mass black holes in the centers of galaxies do. So we haven't really seen them. But on the other hand, we don't know. We figure they must be around because somehow those multi-million solar mass black holes came into being, and the only way we can figure it out is by black holes growing from smaller sizes by swallowing stars and swallowing black holes and whatever they can swallow. But this is the first time we've ever seen something like that.
So the primordial black holes that might have been responsible for merging and forming the black holes at the centers of a lot of galaxies, or perhaps most, if not all large galaxies at least, those primordial black holes, I guess one of the things that I know about stellar astrophysics is that population 3 stars, which were the first stars in the universe, could have been massive enough that they directly collapsed into black holes without exploding as supernovas. So they could have taken essentially all their mass with them and directly metamorphosed into black holes, some of the most massive population 3 stars. Does that comport with what you know?
Well, that may be where these, where these 100 solar mass black holes come from.
Yeah.
The problem is that we have no observational evidence for this process. But at least we've now seen some heavier black holes, not the supermassive, but we've now seen black holes in the 100 solar mass range, which we've never seen before. And, if we can keep observing such things, we can get an idea of what the population is like, and we can test theories of the evolution of the population against what we see. And maybe we can figure this stuff out.
Okay. Great. And so some of the earliest evidence for black holes that humanity discovered, if I remember correctly, was X-rays. And
Yes.
John, didn't you work on some of those X-ray detectors, building some of those technologies and whatnot?
I most certainly did.
Yeah. So why is it, if a black hole is black, how is it that it creates X-rays?
Because the black hole is black, but the matter around it is not. And the matter around it is, as it falls into the black hole, it gets accelerated to extreme velocity. And now all sorts of interesting things can happen when you've got material orbiting a black hole at a substantial fraction of the speed of light. The shear produces a lot of heat. Any entrained magnetic fields get amplified. You get dynamo effects. The dynamo effects eject jets moving at large fractions of the speed of light. So there's a lot of very energetic stuff that happens right in the vicinity of a black hole. The black hole is black, but it energizes the stuff around it. And that is what makes the X-rays and the gamma rays and the radio and, you know, a lot of stuff.
Okay, great. Ivan, I want to make sure that you get on this as well. Do you have anything to add about that, or do you want to, maybe I can throw you a soft question about multi-messenger astronomy, and you can key off of that.
Well, I want to say that John just gave a wonderful explanation of black holes and black hole radiation, so I don't have anything to add to that. As to the question you were going to ask me, throw it and I'll see if I can answer it.
Yeah, so there's this concept of multi-messenger astronomy. And as I know, this is, as far as I know, this is sort of a burgeoning field in astrophysics and astronomy. And could you tell us a little bit about what that means?
So I think what you're referring to is, for example, if there's a supernova, you may see radiation from that supernova, not just in, let's say, the electromagnetic spectrum, but also in neutrinos.
Right.
So you get simultaneous events in different types of detectors. And that can give you more information about what the source is. So some kinds of radiation have more, you have a better idea of where a signal is coming from, because you can look in a telescope, and if you see a bright light, a point of light, which is your supernova, you know that's where the explosion was. Whereas with neutrinos, you're not going to get that same kind of angular resolution. So you might know it came from that way, but
okay.
So it's a way of we'll have models that will predict how much radiation you should see in different forms. And you may also have predictions about when this radiation will reach you. And by getting multiple sources of information, you can maybe figure out which model best fits the data.
Great. And then gravity waves, I assume, would be a whole different category of messenger, as it were.
Yes.
Yeah, I should say gravitational radiation. So I was imprecise in my vocabulary. A gravity wave is actually a disturbance in the atmosphere.
Or the ocean.
Or the ocean, right? It's a fluid phenomena.
Yeah, I misstate it all the time, though. So I know all of physics, and I still say it wrong.
Yeah, I do too. Abby, I got another question for you that has intrigued me for the past year or two. I saw a news story a year or so ago about a brand new organ in the human body that was discovered, and I was wondering if you knew of that reference. And my question is, do you think that there will be additional new organs that we discover in the human body in the future?
Okay, well, as I recall, the organ they were talking about was essentially a lot of distributed soft tissue throughout the body that does a whole lot with how fluids move through the body other than in your circulatory system. I'll back up a moment in order to kind of give you I think, a better concept of this. Most people are familiar with organs like, the liver and the heart and the brain and things like that, where you can kind of point at it and say, there it is, and it'll be one discrete thing to a large degree. But for instance, our skin is considered to be an organ. And granted, we can kind of point to it, but let's face it, it's distributed all over the body. But it functions like an organ in that it has specific things that it does. And this other organ that they were talking about, you can think of it in that way. It's not a lump that you could, sort of take out or stick a sticker in, but rather something that's distributed throughout the interior of our body. But because of the way that fluids moved through it, it looked like it had some unanticipated functions in living organisms. This is where anatomy and physiology can get a little confusing, because anatomically, if you just looked at slices, at that point, the cells are dead and it's not particularly clear what they do other than be there. Whereas when you look, as I said, at how they act in a live body, then you see that there are interesting things happening. And you say, oh, look at that function. Okay, and so organs tend to have specific kinds of tissues and specific kinds of functions. We had seen the specific tissues before, but when it turned out that they had this kind of function, then people were positing at least that this counted as a new organ. And you can argue about whether that counts or not, but that's what they were talking about. Sorry?
I had heard that the mesentery was described sort of as being a construct that held everything together, and essentially from the lungs down, it was the binding organ that kept everything in place, and the cartilage and everything else attached off of that. Is
like
that
a scaffold?
What you were hearing?
Well, what was the name that you used there?
Mesentery. I think it's MYSENTERIE.
Could be. Okay. Okay. That I'm not sure of that name. Hang on, I'm going to mute myself because I've got a plane going over.
Wow.
Hanscom is as Hanscom does.
Yeah, that reminds me, talking about the functional aspects of cells in our body versus a structural role. I'm familiar with some articles that talked about the astrocytes in the brain.
Mm-hmm.
So conventional wisdom is that the astrocytes are almost literally a scaffolding that provides a geometric pattern that the neurons can sort of travel along, and it helps support the neurons, but isn't implicated in any cognitive processes. But then a while back, I saw some news stories indicating that the astrocyte cells were actually involved in cognition to a certain extent, or at least in regulation of neurons. And so they may have not just a structural role to play, but also a physiological, or in a somewhat more removed context, certainly neurological and role in consciousness and cognition.
Okay, I was interested in, you were using the term mesentery, Okay. As I said, I did not recall the name of the organ or whether that's the same thing that I read about, because I do remember reading about this. Now, there is a structure in the abdomen called the mesentery.
Yes.
Which has been known forever, and that is actually something that you can kind of stick a probe into. And that is something that it's basically a tough membrane that grabs onto your intestines and anchors them onto the dorsal body wall so that they don't just slosh around inside your abdomen. And they also contain a lot of blood vessels. So anytime that you hear about blood vessels going to your digestive system and absorbing nutrients, those blood vessels are all buried in the mesentery. That's how they get where they're going. They absorb nutrients there. They bring the nutrient-rich blood eventually to the hepatic portal vein and the like. But so the mesentery is not the same thing as this thing you were talking about, the mesentery.
I'm sorry, my spelling was terrible.
No. As I said, it's entirely possible that this is something brand new. I had not heard the term mesentery before, and it may be the name that they gave to this putative organ, but I hadn't seen that term before. So I'm just trying to put a little bit of clarity on what the mesentery is or is not, if that makes sense.
The mesentery,
E-N.
E-N, has been known for a while. Right?
The mesentery's been around forever.
Okay.
I mean, that's something that's easy to find, actually. That's something in any abdominal dissection, you can point to it very, very easily.
Yeah, I don't
dissecting it out of frogs in high school biology.
Exactly. It's one of those things that's very easy to point out. Now, as I said, I had not heard the term mesentery before, and maybe that's the name that they're giving to this new putative organ, but I'm not sure. Now, in terms of your question about are we going to find more organs, we may find more distributed things like that. I mean, we always keep finding out that things are more complicated than we thought they were. We're certainly, I mean, if I were sort of cornered and forced to put odds on something, I would say we will find more hormones. So we will therefore find more endocrine secreting glands. Now, they may be distributed. They may not be something like the pancreas, where you can say, again, you can point at it and stick a probe it and say there's the pancreas. But we keep finding more hormones, and usually the cells for them will be distributed, say, throughout the digestive system and things like that. So we might find stuff like that.
Yeah, I had heard it described as saying that although we had seen it before, no one had recognized the entire structure as being a single entity. And
Well,
that this is going to have a lot of effect on surgeries in the future as we think about, just slashing through it and saying to hell with it. This is going to say, oh, this is something else that we should take care of in the process. We just can't slash it open. We have to incise it. And then when we're closing back up, we have to think about doing it properly rather than just saying, oh, it'll heal.
that's really interesting. So a little bit like, say, the water table.
Yeah.
You disrupt the water table and things might be very different and problematic. And that is something that we keep finding out about surgery, is that there are better and worse ways to cut people open and sew people up. No, I mean, one example that I kind of love, which is, not that one, which I'm interested to hear about, but on your skin, we have a lot of elastic fibers in our skin. And, they tend to run parallel to one another in bunches, and then there will be, another bunch that goes parallel in a different way. And we've got those things pretty well mapped out now. And what this means in terms of cutting to get inside is that there are better and worse ways to cut.
Huh.
That, if you have fibers running in parallel and you cut here, these are elastic fibers, okay? So if I cut here, the elastic fibers are going to do this, and it's going to be much harder to heal. Whereas if I cut like this, the elasticity will actually help close the wound a little bit later on. So, you know, I wouldn't be surprised if, again, with this, you know, sort of this other fluid dispersing organ, that I wouldn't be surprised that you're right, that there are better and worse ways of putting that back together or cutting it in the first place that would help with healing. Again, that's not, we keep discovering things like this, and it's just a matter of slowly working it out.
Oh, I wanted to go back to the physics thing that I read just recently. We've all heard about the longevity of the black hole, that something being on the order of 10 to the 76 years. And when I heard that at Fermilab, I had to take a long time to think about it, in that, you know, our universe has been around for 10 to the 10th years. So that's one universe, and then you have to do it again, and then you have to do it again and again and again to get to your 10 to the 70th. And that was a really long time. And I'm going, wow, that's like the end of the universe. Well, just recently, a mathematician came up with the idea that the universe really dies when everything is iron 56. Nothing can happen at that point. You got iron. And it would be spread out over space. So essentially, there's little balls of iron at almost infinite distances from another. And that's what he called the end of the universe. And and his mathematics said it's 10 to the 32,000 years. And I figured that's a really long time.
Well, now I want to know more. This is really interesting. So when you have little balls of iron at great distances to one another, then it's all over. Is that what?
Yeah, because iron can't do anything. It can't burn.
Uh-huh.
So there's no possibility of making stars or galaxies or anything else. It's just, it's over.
Yep.
Bye. So I'm going 10 to 32,000 years.
It can clump together and collapse into black holes.
But at that point, I don't know what happened. So that was his mathematics. And I'll let you two physicists look that up and go.
Yeah, you know.
Probably.
I'm an experimenter. If I can't pick up something like this and figure it out, I'm not interested.
I'm assuming there was some assumption about dark energy expanding.
Yeah.
The runaway expansion or something.
So
I started reading it, and the math just went whee. So I said, let Ivan and John figure that out. That's not me.
So the article I read about that is that it's essentially quantum tunneling over quintillions of septillions of billions of trillions of years, or something like 10 to the 30 to the 1,000 years, a huge number.
It's ridiculous.
And eventually there's enough, even at a relatively cold temperature inside of neutron stars, there's enough quantum tunneling happening that it can lead to an instability in the material of the neutron star. Maybe it was a white dwarf, but in any case, it's one of the collapsars, and over time it builds up a differentiation in the material deep inside because of quantum tunneling effects, and that differentiation in the material composition leads to a physical instability that might instigate a supernova. The object itself might undergo a catastrophic sudden collapse and then rebound. So these supernovas might end up being the last interesting thing that ever occur in our universe in something like 10 to the 30 to the 1,000 years from now.
And that's it. We just end up with a nothing.
Yeah. Well, so there's this wonderful idea by Roger Penrose, and I wrote about this in my book. Roger Penrose believes that he's found some mathematical justification for positing that the very distant future universe will be similar topologically and in terms of energy distribution and physical characteristics. It'll be indistinguishable from the early universe that gave rise to the Big Bang. So he has come up with this notion of a cyclic cosmos, where when our universe expands arbitrarily large and becomes so incredibly rarefied that it's structureless, it becomes homologous with the universe, the state of the universe that birthed the Big Bang. Not a lot of other physicists and readings that I've done corroborate that, or his mathematics may be perfectly sound, but his idea about the physics of it all is not something that a lot of people have bought into. But for those who are looking for hope that the far, far distant future of our universe might lead to something interesting happening, well, we've got those supernovas that I mentioned, and then maybe, just maybe, it can be the womb for birthing new universes.
An interesting hypothesis. How would you test it?
Well, yes, there is that. Well, that makes me think of the whole multiverse idea. But before I open up that can of worms, I wanted to say that our trusty moderator Dave was able to do some web searching while we were talking, and he found that the new organ from 2018 is called the interstitium, and it's a fluid-filled spaces were found within the body's connective tissue that seem to have a physiological sort of unified function. It's the interstitium.
Between the spaces.
I gotta hear it. Okay, so that would be S-T-I-T-I-U-M, right? Interstitium?
Yeah.
Yeah. Very nice. Okay, interstitial fluid is the fluid between your cells. And the fluid between your cells is some of the most important stuff out there. That's really where everything happens in some respects.
Oh.
This is where nutrients get delivered to cells. This is where wastes get taken away from cells. It's where fluid coming from the blood flows through your, or not through, but around your cells. And then eventually some of it winds up back in your blood, some of it winds up in your lymphatic system. Eventually it gets recycled back into your blood, except for a little bit that winds up going through your kidney and being excreted. But so the interstitium is as I said, I kind of used the idea of a water table with a certain amount of forethought. You know, you can kind of think of it like the water table in your body. It's where you have all this stuff flowing through, all this fluid flowing through, going from your blood, bathing your cells so that your cells get what they need. The cells, meanwhile, are getting their wastes taken away, but on the other hand, in some cases, they're also cranking out hormones, for instance, and other things that you may need. And they eventually get recycled. The fluid eventually winds up back in your blood if you wait long enough. And basically, we had seen, as I said, plenty of those cells before, but we had not thought much about the flow. And so that's what they were positing, is that although we could see those cells, you know, forever, we didn't realize quite how complicated the whole flowing was. And so they were positing that it functions like an organ, if that makes sense.
Okay. How does that differ, what you were describing, Abby? How does that differ from your lymph system?
Okay. Lymphatic system is kind of fun. What happens is this, and I mean, there's a bunch, as with so many things, it's like there's a bunch of different things going on. Thing one about your lymphatic system is, remember what, again, think about practically the first thing you ever learned, if you learned anything about anatomy and physiology, is that, you know, your blood vessels take up nutrients from your digestive system, and then they get delivered to your cells. And there's a certain amount of not really thinking about the idea that somehow those nutrients have to get out of your blood vessels and to your cells. And so that is where there is fluid exiting your blood vessels. And let's say it's nice nutrient-rich fluid. It's got oxygen in it. If it just came from the lungs, let's say. So this fluid then flows around your cells. But then what happens, right? Okay, so the fluid has left your circulatory system. Now what? And the answer is some of it gets back into your circulatory system fairly quickly, but a lot of it winds up in this completely separate bunch of tubes called the lymphatic system. You can think of it almost like a second circulatory system, sort of, kind of.
Is it driven by your heart as well? Does the heart pump the lymphatic system?
Oh, that's the problem, is that the lymphatic system doesn't have a pump other than every muscle you've got in your body. So when you, basically, it's a whole bunch of one-way tubes. So the fluid winds up in these tubes, and when the tubes get squished because your muscles are working, the fluid can only go one way through these tubes. And eventually the fluid winds up, kind of up here, where it eventually gets dumped back into your regular circulatory system that has blood in it. But that whole lymphatic system, basically the fluid only gets where it's going by way of being squished because your muscles are working. And this is why people, as they age, can wind up with a lot of fluid in their legs. It's because, you know, when you're younger and you're doing lots of muscle stuff, the fluid gets pushed up more, and it works a lot less well as people age.
This is why after this finishes, I'm going out for a walk.
Right. But then the other thing that the lymphatic system does is, okay, now think about the problem that you've got here. So you have this way of delivering fluid that has flowed through all of your tissues, going back into your circulatory system. You can probably spot a potential problem there. What if some of those tissues are infected? Now suddenly you have this fluid, which may have bad bacteria in it, going into your lymphatic system, going up to your circulatory system, and being spread all over your body. Oh boy, just what we want. So you've got to clean this stuff up, and that is where your lymph nodes come in. Lymph nodes are infection fighters, and they are sort of stationed throughout your lymphatic system. And your biggest lymphatic organ is your spleen, which is another one of those things that you can find easily in an abdominal dissection. Some people confuse it with another chunk of the liver, but it's not. It's the spleen, which is, as I said, a large lymphatic organ. But anyway, so in the lymphatic system, you have this secondary set of tubes for getting your interstitial fluid back into your circulatory system. And as I said, the fluid gets cleaned up along the way because you've got all those lymph nodes there.
So our moderator and fellow science enthusiast, Dave, did some research to look up that new discovered organ, the interstitium. And according to the article I was reading or scanning while you were talking, apologies for my multitasking, it's entailed in interstices within connective tissue that were not previously known.
Okay.
And it's in these fluid-filled gaps in connective tissue that might be a source where lymph fluid actually gets generated.
Mm-hmm.
And it might have implications for things like the spread of cancer. Might travel through these previously unknown fluid-filled spaces or sacs within connective tissue that previously, I guess the thinking was that the connective tissue was connective tissue and not gaps in it that were fluid-filled and might have a physiological role.
That's really interesting. And the other thing about that is that connective tissue is it's what you have the most of in your body. It's very widely distributed, and you've got more connective tissue than anything else. It is literally what holds us together. But I can see how, yes, if you could kind of identify little interstices in it that had fluid in it, that they might have some that they might have some functions we hadn't thought about. That's interesting.
Yeah. So the larger, sort of the theme, I guess we've been playing with during today's conversation is new discoveries about things that science has otherwise known a lot about for hundreds of years, if not decades. New kinds of black holes, new kinds of functions for existing tissues, new organ in the body. I guess if I could draw a larger theme out of that, it would be that we've sometimes treat science as if it were an encyclopedia that's written and done. And those of you who are or have previously been working on the forefronts of research are constantly discovering new things, new ways to get information about the natural world, new aspects of the natural world. And I draw a contrast between that and a dogmatic view. Some people, I think, believe or behave as if science is dogmatism. This is what the science tells us. And that may be true in some cases, but there's some real distinctions between science and dogma. Again, I have to appeal to the most familiar dogma to most people, which is maybe a superstition like horoscopes, or maybe a superstition based on a traditional religion. Those kinds of endeavors, although you can spend an arbitrary amount of intellectual time dealing with them, they don't seem as willing to expand their horizons and discover new things as real science does. So any of you want to talk about that or expand on that theme?
Sure. Out at the cutting edge, you're often wrong. You got to get used to it.
Yes.
Okay. You can't say, oh, science says this when you're out at the cutting edge. Yeah, the other thing is that I hear all this angst about the end of physics.
Yeah.
I see lots of physics happening. I do see that it's getting very hard to find new physics with synchrotrons. So do something else.
Yeah. I think this comes back to one of the points that's constantly made about science is, well, you guys don't know anything. You're always changing your mind. And that, of course, has nothing to do with it. We're constantly discovering new and interesting things. And so we have to go back into history and say, oh, what we thought was true is still true, but we have to add this in here now, or we have to subtract this, or there's a slight change here. But we're constantly building a structure and constantly coming up with new ideas and new constructs that add to the structure. And so, yes, it's constantly changing. If we look back at Galileo and Bacon and such, what was science then in comparison with what we're doing now? If they saw a simple telephone, the things that we all carry around in our pockets, it would be black magic. We'd all be hanged.
Right. Yeah.
And one of the things that happens sometimes is if there's a very small effect, or perhaps no effect, it doesn't mean to say that you'll never see a positive result, right? So let's suppose that you come up with a new therapy or an old therapy, and you're testing it, and you test it on patients. If there are enough studies, one of them is going to be positive just by chance. And then you retest it, and then you get a null result. And it's like, and if, of course, the newspapers will report that here's a study that says that this therapy works, and then the next study says, no, it doesn't. And so what you'll expect, if there's no effect, is to see this sort of oscillation where a therapy appears to work or it doesn't. Or it could be diet, right?
Right.
The effect of like should we be eating eggs? What is the connection between eggs and heart disease? The theory was that eggs contain a lot of cholesterol. Cholesterol is correlated with heart disease. So if you eat eggs, maybe that's bad for your heart, which was not terrible reasoning. But of course, the problem is that just saying this on paper, looking at ingredients, looking at what's in test tubes, is not the same thing as looking at what happens in patients. And it turns out that although we do absorb some cholesterol from food, we don't absorb most of it. And I believe that the latest meta study that I read about said that if you eat an egg a day or 6 eggs a week, something like that, that your risk of heart disease goes up 6%. So it's a small effect. So you can imagine that studies that were done, some of them just by chance would show enough of a correlation to say, oh, eggs raise your risk of heart disease significantly, whereas others would show no effect.
Mm-hmm.
So this is also something where, like John says, when you're on the bleeding edge, sometimes you're at the limit of what your instruments can tell you, or the limit of what your experimental studies, the amount of data that you have is not enough to tell you the correct answer. And so the numbers may oscillate back and forth. So when the press reports things, it's very important to look at how many people were in the study, what kind of study was it? Was it well controlled? Was it just observational, and so on?
So that brings to mind also the issue of complexity. As the systems we're studying become more and more complex, the level of certainty that we can justify in our conclusions becomes less and less. Whether it's physiology or climate or human consciousness, or even the workings of a single cell are so phenomenally complex that I don't believe anybody can confidently assert that they have figured it out. And we're constantly discovering new things. We do have a question though that was posted on our YouTube chat that I want to throw into the forum, and that is, what about the power of positive thinking on human health and healing? Does anybody have an idea about that?
Oh, I'm going to say it's important. So there.
Yeah. Well,
Well, we all know that when you're depressed, for whatever reason that occurs, you don't get up, you don't do things, the entire world seems blah, and you yourself fall into a trap. And it's sort of a death spiral as you go down. Whereas if you have the positive, you tend to get your way out of it. And so the mental attitude drives your physical activities. And now you have a positive physical activity, a positive mental activity. You're going to go out and do more things.
get your lymph system going. Yeah, you'll get your lymph system going, as we said
you need
earlier.
the lymph system going.
Well, as I told you when we were starting up, my surgeon says my broken ankle is 6 months ahead of normal schedule healing for my age. And I attribute it to the fact that I'm getting up and walking 3 miles every day.
Yep.
There you go. One of the other things that this question brings to mind is the placebo effect. There have been countless studies that show a positive health outcome correlated with any manner of placebos. It can be something as counterintuitive to us scientist types as having people, wave mumbo jumbo in your general direction, to giving somebody sugar pills. Then there have even been studies, if I'm remembering correctly, where people in the study were given a placebo and told that they were being given a placebo, and yet their health outcomes, statistically speaking, compared to participants who did not receive the placebo or the information, was better. So there, from what I've read, and this is probably a year and a half or 2 years old when I was looking into this, the answer about why expectations around positive outcomes and the placebo effect in general, why that has correlation with better health outcomes is still a mystery, right? It's not yet been solved. But there's enough statistical evidence to show that it's a real effect, but it's one of those black boxes currently.
Well, there's also some cool stuff. I remember at this point, it must be, maybe 15 years ago or so, Scientific American had a really great series of articles or bunch of articles all tied together in one issue, which was about the brain. And so it wasn't just one, but it was sort of like almost like a jigsaw puzzle, a bunch of different articles that obviously, since they were about the brain, there were some things that related. And I do remember reading then that, for instance, the part of the brain that is called the hippocampus is a part of what, regulates our emotions and does various other things as well. And that it is also a part of the brain that is plastic, meaning it can change. And it's one of the parts of the brain where you can actually get new cells. You talk about science changing. When I was in high school and I think even in college, we thought that once you had developed as, an adult, you had all the neurons you were ever going to get, and it was all downhill from there. Now we know that sometimes we do get new neurons, at least of some sorts. And there was some pretty good evidence in these bunches of different articles that I read, saying that basically there are places where these new neurons are made, and that depending upon how you are sort of feeling and thinking about and doing at the time, you may have more or fewer of them made, and more or fewer of them may migrate to the hippocampus where you really need them. And that if you have more new cells in your hippocampus, then you're going to be overall better off, particularly sort of emotionally and psychologically. And so it was this very interesting, interfeeding, interconnected bunch of things going on. And I remember, one of the take-homes that I developed out of that whole series of articles was take care of your hippocampus, which means in part, as the questioner was saying, that positive thinking and putting good things into your brain, and that can include exercise. Exercise is known to have a very good effect on our overall mood. Getting enough sunlight is well known to be correlated with having a better mood. Exercise, sleep, all of those kinds of good things can genuinely help with our mood, which in turn helps these new brain cells to generate and migrate to the hippocampus, which makes us feel better. So as Joanne was saying, it is very much a virtuous circle when it's going in the right direction. And we do actually have some physiological evidence for that. And if I could remember the issue of Scientific American that it was in, I would tell you, but I don't remember.
We know that the brain has an impact on hormones and cortisol and just general chemistry of the body, that our cognition extends beyond the brain. Mm-hmm. So it's not like it's a magical effect, but it is very complicated and complex. So it's difficult to see exactly what the connections are. But for example, the statistic I heard was that a lot of like over-the-counter pain relief pills, when they test them, of course they do test them with placebos, and the placebos do quite well in comparison. They're not as effective, but there is a real effect there. Mm-hmm.
And there are feedbacks. I swear that when I have a tough math problem that's puzzling me and I can't figure it out, best thing to do is get up and do something.
Yes.
Mm-hmm. Walk, chop wood, ride a bike, something like that. And the answer will come to me.
Even sleep on it.
Yeah, that works too. I figured out something last night at 3 o'clock in the morning. That does work.
I have a pad of paper and a pen right by next to my bed. So when I come up with one of those brilliant ideas, I write it down because
Yeah,
7 or 8 o'clock in the morning, you will forget it. It just won't happen.
right. Well, this is also why when I'm writing something, I have what I call the rolling outline style of writing, where if I want to write something and I've kind of got it figured out what I want to say, or maybe I don't, but I've got some ideas, I'll basically put it down in a file as an outline. And then it's there. And a colleague of mine told me that if you want to get something written, and he wrote many books, so I figured he knew what he was talking about. He said, write 10 minutes a day. I mean, you can write more than that, but just commit to 10 minutes a day if you're writing a book or something like that. And so I have done that, and I have found that that does really work, essentially because it keeps it fresh in my mind. And when I, just go back to where I was yesterday and I look at things, I write a little bit. But as I said, the magic was what Joanne was talking about, that wherever I had gotten to, if I hadn't quite figured out what I wanted to say next or how I wanted to say it, next day, I come back to it. Very often I figured out how to say it by then. Move along a bit further, stop for the day, and again, by the next day, I have figured out what I want to say for the next bit. So it's this rather nice little engine for keeping the whole thing going.
It works.
It does.
And then every once in a while, you find stuff dripping off your fingers, and you look up, and it's midnight, and you realize that you've just written a heck of a lot.
Oh yeah, I didn't say only 10 minutes a
Yeah,
day.
right.
That gets you in your chair.
Right.
And then at that point, maybe you write a half an hour, or as you said, the next thing you know, it's midnight and it's like, oh, well, I got a lot done. Cool. Bedtime.
Yeah, I face the same thing when I when I sit down to write. Sometimes I'll have an idea that I think is going to take me half an hour to flesh out, and 6 hours later I'm still writing. So not necessarily on the same idea either, but it's just like you said, once you get started, sometimes it's hard to stop.
And sometimes in cases like that, what I will do is, again, just try to, if it's midnight and I've still got a lot of good ideas, put it down as an outline so that when I come back to it the next day, I can say, oh, yeah, right, that's what I was talking about. At least it's still there, sort of, kind of, if I get back to it soon enough, because at that point it's in my own private language and there are a few words that stand for a whole lot, but it can then kind of be fleshed out for people who are not me.
Right. So I want to get back to something that John mentioned a few minutes ago, which is collecting evidence about various scientific propositions and whatnot. I have an example of something that I think might be a useful seed to start a discussion about evidence and what constitutes evidence, etc. And once again, I refer back to my favorite topic, astrophysics. And specifically, there's all kinds of science about what happens in the centers of stars, the fusion processes and the material constituents and the convective versus radiative heat flows and whatnot. Lots of scientific ideas about what happens in the centers of stars. But there is no conceivable mechanism that we could ever deploy or employ that could actually take us to an observing point inside a star. All materials that we are familiar with, all chemicals, all mechanical constructs would be turned into plasma as we got close to, much less inside a star. So I was wondering, Joanne and Ivan and John, Abby, feel free to to chip in also. How do we parse? How do we think about situations like that where we can't even conceivably get any evidence, and yet science claims to have a lot of knowledge about this inaccessible realm?
Actually, we can look into stars two different ways. Neutrinos. We see neutrinos coming out of the sun, so we can observe their spectrum even these days, the number of neutrinos. It turns out that our theoretical understanding of what was going on there in the beginning was better than our understanding of neutrino physics, because what we wound up discovering was neutrino oscillations. We didn't learn very much about the sun. And there has been one look inside a neutron star using neutrinos, supernova 1987A, when it first collapsed into a neutron star, was extremely hot and was making neutrinos, and what the Kamiokande experiment saw 20 some odd neutrinos from it. And that actually told us quite a bit about what happened there. So yes, we can see inside stars with neutrinos. But now, up here is an image from the TESS space mission, which I'm deeply involved in. And TESS is primarily looking for exoplanets, but we have a very large secondary mission, which is helioseismology. And I should say asteroseismology, the correct term for stars, yes. And so we take photometric measurements of stars. Those targets we look at every 20 seconds, and we look at how they vibrate. And the sound waves that we're seeing go all the way through the stars. And so we're seeing evidence of all the structure of the star, and the theorists who look at this data can tease out things like how deep the convection region is and things like that. It's just like looking inside the Earth with earthquakes.
Yeah, that's another great analog is, we can't send a probe into the center of the Earth, and yet scientists are very confident that the center of the Earth is an iron nickel blob. So it's an analogous situation where scientists have a great deal of knowledge about a physically inaccessible realm. So Ivan, you were going to say something too?
Yeah, I was going to talk about the Bayesian approach to theories and evidence, which is that if you're trying to decide which of several theories best fits the evidence, well, if those theories make predictions about the evidence, that's enough to get you inference as to which theory is more likely to be true given the new evidence that you've received. So if you were looking at neutrinos from stars, for example, the reason that allows you to see in there is that we have models of what happens in stars, and those models make predictions about what neutrinos you should see. So when you observe the neutrinos, that tells you something about which theory is more likely to be true. So this is a general result. So any time where you have a theory that makes predictions about evidence, and the evidence can be removed. It could be removed by millions of years from the original event. So evolutionary
millions
biology,
of kilometers, right? Or
right?
Thousands of kilometers, right?
Yeah, evolutionary biology makes predictions, and it's because we've looked at the DNA of life on Earth, for example, that evolutionary biology makes predictions about that. That's the reason why we now know that the theory is true.
Yeah, in chemistry, as a for instance, we look at a molecule and we say, how is this structure put together? What is involved? We can do some basic physical chemistry where we actually burn an organic material and find out how much carbon and oxygen and nitrogen is there, but it doesn't tell us the structure. However, if we take, for instance, a thin sheet of material and look at it with a heat spectrum, and look at the heat that's coming through it. Some of the heat will be absorbed and some of the heat will pass through unabsorbed. And if you make a spectrum of that, you actually see where carbon and hydrogen are just bouncing back and forth. The little teeny hydrogen is bouncing back and forth at a very high speed on the relatively larger carbon. Or you can see a place where the carbon and an oxygen are bouncing back and forth, or twisting, or turning. And you can see these those these areas where heat is absorbed by the molecule itself. And we use this as a diagnostic. We can say, what is the frequency of the hydrogen atom bouncing up and down on the carbon atom? We actually can measure them. We know how big the carbon is, we know how big the hydrogen is, we know how the bond is, and we can actually calculate it. Look at it in the spectrum and go, aha, that is a carbon with two hydrogens. Aha, that's a carbon with three hydrogens. That's a carbon attached to an oxygen. And we can actually build backwards from this, seeing how many oxygens, how many hydrogens are all together in their structures to form an idea of what this molecule actually looks like, what's connected to what and in what order. So we've used an indirect approach to find out something that we actually can't see, but we have evidence. And if we now take that evidence and go to the next stage and say, aha, I know this is true, therefore we will be able to do this. If it works, you go, aha, I was right. And now after 100 150 years of pushing uh, infrared energy through objects, we just understand infrared spectroscopy is a wonderful tool to look at structures of especially organic materials, and it's indirect. And we're using these indirect approaches because they work. And we can go backwards in time. We can look at it in the past. We can carry it forward to the future. We can do the if then. If this is true, then that is true. And we build up this body of evidence, and such that we're looking at neutrinos in the sun. We're looking at the expansion of the universe. We're looking at black holes coming together. All of this is indirect evidence, but we have built these fabulous machines they can take our senses and expand them to the size of the universe or to the size of an atom and
Right.
allow us to view the entire universe. It's cool.
You know, your description reminds me of a very simplistic, you know, pardon me for trying to be simple on something as complicated as infrared spectroscopy. But if I'm walking through the woods and I hear the call of a blue jay, then I can be really confident that there's a blue jay out there somewhere. I don't have to see it. I don't have to dissect it. I don't have to hold it in my hand. So sometimes the signals emitted by physical entities and processes, the signals that come out of those and off of those constitutes a great deal of evidence that we can use to identify them uniquely.
It's in astronomy, we're famous for taking very pretty pictures. But the truth is that we tend to learn more about what's going on out there from spectroscopy than anything else, because spectroscopy tells us what things are made of, how hot it is, how dense it is, how fast it's moving. It's our really most powerful tool. But it's also our least photogenic tool. It's not the one that we show to people who aren't astronomers, because it's hard to, it's not beautiful to someone who's not used to looking at it.
If I show someone an infrared spectrograph, infrared spectrogram, it's just squiggles on a piece of paper.
Yeah, right.
And they go, what's that? You go, oh, well, that's carbon hydrogen. That's a carbon oxygen. It's probably a carbonyl. And they go, how do you do that? And you go, yeah, I learned.
Well, it's a lot different than physiology, you know, Abby's specialty, where she can, you know, take an organ or a tissue and hold it and see it and manipulate it and poke it, etc.
Well, that's the easy part.
Yeah. What are some of the more complicated ways that you investigate questions in physiology?
Well, as I said, when you start getting into systems, and as you were saying, when you start getting into the chemistry of things, that's where things start getting complicated. An easy example of something that we can't see because they're too darn small would be something like how proteins are shaped. And proteins, as molecules go, are huge and very complicated in their own right, and they have all kinds of structures that are incredibly important to their biological function. And this is one of the things that I find kind of cool, is that, I mean, proteins are made out of amino acids. And we've only got, depending upon who you ask, like between 20 and 22 amino acids. All of proteins are just made out of these things. And here's the part that is, to me, interesting. You can sequence a protein. You know the actual, which amino acid comes after which, this kind of thing. You can sequence the protein, and that still does not tell you its biological activity, because it's only the amino acid sequence. What makes proteins biologically active and interesting and useful is how they fold up on themselves. So instead of having like just a chain of amino acids, they fold all around and do all kinds of peculiar things like this. And that's actually what makes them interesting and useful to us physiologically. The shape of the protein is absolutely everything, to the point where if the shape is destroyed, as can happen by cooking, this is why raw meat looks different from cooked meat, for instance. If the shape is destroyed by cooking or by whatever, that is called a denatured protein. It's no longer biologically active. Sometimes they recover, sometimes they don't. But the kind of the easiest way to think about this to get people started is, let's talk for a moment about receptor proteins, which are found inside cells and also on the outer surfaces of cells. So you have these receptor proteins that are often very specific to something, let's say a hormone. So we have these receptor proteins that have a particular shape and no other, sitting on the outside of a cell membrane looking out. And what happens is, let's say it's a hormone effect for a moment. What you are doing is that you have this particularly shaped receptor protein that is like a lock on a door. And this is a pretty good analogy in a bunch of different ways, because of course a lock has a particular shape. But if you open the door, that enables a whole lot more things to go on. You can enter the room and do whatever you're going to do in the room. But you've got to get through that lock. And what happens with, say, a hormone, but it goes for lots and lots of things, is that the hormone is the exact right shape to go into that lock. It's like a key. And so a key has to, be roughly the correct material, but it has to be the correct material in the correct shape, or it won't work. But if you have the correct lock and the correct key, and they go together, and you turn the lock, then that enables a whole bunch of other things. And that goes for hormones, but it goes also for how your nervous system works. Down at the very bottom of getting a nerve signal from one neuron to the next neuron, or from a neuron to a muscle, all of that is based on protein receptors having a particular shape. Mess up the shape, the whole thing is messed up. How do we know that? It's certainly not because we can look at them.
There's several diseases, like prion diseases and whatnot, that are related to proteins that have acquired the wrong shape. And sometimes they meet other proteins of the same chemical structure, and and they can transfer the misaligned shape property to to other proteins, and so it spreads throughout the organism. This sort of catastrophic phase change in the geometry of proteins.
Rebending or different bending of a protein. Yeah. Mm-hmm.
Yeah. Well, I've got a doozy of a question in the chat. We may not be able to delve terribly far into the answer to this question or thinking about this question in our remaining 8 minutes or so. But I wanted to throw the question out there, and then we can potentially pick it up again next time. The question comes to us, if the universe essentially ends up with blobs of metal that are very, very far apart, wouldn't all energy in the universe be equal? And then doesn't that also mean that time would stop? How do you conduct experiments when time has stopped? So that's the question from YouTube. I could take a stab at it, but I'll let our professional physicists go first.
Well, for years we've talked about the heat death of the universe, where indeed you wind up with a universe which is all at a constant temperature. And yes, that's basically what happens. Time doesn't stop in the sense that things are still moving around, but there's no thermodynamic energy that you can use to energize a machine to make an observation. Every time we make an observation, we use some sort of machine. And if you look carefully at how our physical machinery works and how our selves work, entropy is generated during that process. And once you've reached the heat death, the universe has reached a state of maximum entropy, and it's not possible to generate entropy anymore. So it's not possible to do these irreversible processes that constitute measurement or cognition. So yes, in that sense, time stops. In the sense of things moving around, dynamical time doesn't stop, but thermodynamic time does.
Ivan, do you have perspective on that as well?
No, I agree with John. Sometimes the arrow of time is associated with entropy. But if you are in a state where there's no free energy and everything is in equilibrium, there's, as John says, there's no way to store any memory. You can't do any work. So there over a certain time span, you could say that, well, I can't really tell the difference between the past and the future, but it doesn't mean that nothing is moving around.
Yeah, things might still be orbiting each other, for example. Black holes in the distant future might still be slowly spiraling together, for example.
Right.
Well, even that generates entropy, though. If you've really reached the heat death, you've reached the point where you're generating negligible entropy.
Yeah. So a lot of
if we have a black hole, we know that it is dissipating. We know that it's going to disappear over time, and so that's an energy that exists, and we haven't gone downhill to a zero to infinite entropy. So as long as black holes exist, then there's going to be some measure that we can cause the time. But when the last black hole disappears, there's nothing.
Yeah, I think if I remember correctly, black holes are entities with maximal entropy to begin with. And so when a black hole dissipates, it doesn't add to the entropy in the universe. It just transfers from one status to another.
If the black hole, again, we're getting into theory that
Here we go.
that cannot be tested. We think we understand Hawking radiation, and if the universe has become so dilute that the temperature of the universe is below the temperature of a black hole, then the black hole will start to evaporate. And in fact, it has a temperature and it will warm the universe.
Okay.
And as black holes evaporate, they get hotter, which means that they evaporate faster. And so, yes, Joanne's right. If you have black holes, they will restore the temperature gradients that make things possible. But once they've all evaporated and everything has dissipated and you've had thermalization of the resulting radiation, then you've reached the heat death. But
Yep.
this is now we're getting into extreme theory that I'm not terribly comfortable with, because I'm an experimenter. I'm an instrument designer. That's what I do. And I can't design an instrument to probe this, so I don't know.
So what does the spectrum of nothing look like?
I mean, even if you have evaporating black holes, it's not like you're going to be basking in a glow.
No,
Things.
no.
It's so little
And so far
radiation
apart.
that it's unlikely you'll be able to power. You wouldn't be able to power an FM radio or anything.
Nope.
So.
All right. Well, we're about out of time for today. This has been another delightful, protracted conversation on many different science topics. Today's conversation is made possible in part by a grant from the American Humanist Association, and all of us who are participating in your panel of science communicators and scientists are associated with the American Humanist Association. And specifically, this is a project that has been launched by the Prairie State Humanists from a suburb of Chicago. So thanks everybody who tuned in. Thanks to our panelists. Anybody have any parting words before we sign off?
Bye, everyone. See you in a couple of weeks.
Yeah, we'll be back in a couple weeks.
Stay healthy.
Yeah, stay healthy, definitely.
Thanks.
Bye. all.
Bye.
Wait, we got Dave says, wait a second. We got 2 questions on YouTube. Wow.
Okay.
Can we hang in here for another couple minutes?
Sure.
Okay. Let me pull my laptop closer so I can read the questions better. One of our YouTube viewers has said that in a finance, for example, an over-reliance on positive thinking in place of careful preparation and realism will continue to bring us down. So, being realistic, I guess, is important.
So that doesn't have to do with physiology.
That's right.
That's science. You test your brain, whatever your brain says, against reality.
Yep. And then, but I would say, economics is one of the things that I get pretty excited about, and I have at least learned some about. And overly optimistic thinking is a problem. One of the pieces of overly optimistic thinking that seems to be very common among economists is not as much in the current day, but certainly historically, was an assumption that the economy could continue to grow indefinitely. And tying it back to physics again, every element of growth in an economy is related to the generation of some new material, or the transport of material, or the creation of some intellectual property. And all of these things consume energy. And there's a finite amount of energy available to us in our ecosystem, regardless of whether you think about fossil fuels or solar or wind. So the idea that the economy can continue to grow indefinitely and continue consuming energy and dissipating heat, if we grow, I did this calculation once, it's something like if we grow at a modest economic rate of something like 4% a year globally, or 2% a year globally, in a geologically non-trivial amount of time, something like 100,000 years or 10,000 years, that rate of growth will correspond to an energy dissipation rate that would turn the Earth into plasma, the amount of waste heat.
Oops.
So this is a great example of how, you know, thinking about physical reality and the constraints it puts on us and our capabilities is sometimes divorced from our wishful thinking, specifically in the area of finance. And then one more question. There's such a thing as infinite density of mass. Is that a cyclical way of restarting the universe with another Big Bang? So that sounds more like you know, maybe black holes turning into new universes is a naive way to think about that. But do one of you have thoughts about that?
John, I know that you measure singularities every day.
But
Every day.
the theory tells me that the singularity is infinitely far in the future. When you the actual dynamics of a black hole are such that there is no singularity in there right now. You have to wait forever for the singularity to form. Now, it's true that the surface of the star that collapsed is receding from us at the speed of light almost. And so it's dark and it's black and all that. And the math says that it reaches a singularity, but there's no way to verify that. And the math says that the singularity is infinitely far in the future. So in fact, I don't get to study singularities. I get to study the surroundings of what might someday be singularities.
Right.
Great point. Yeah, and then string theory also might be a way, give us wiggle room, so to speak, from the idea of an infinitely dense singularity or point of mass, that maybe strings cannot be compressed, and there could be a loop, for example, a loop of string material at the centers of black holes rather than a literal geometric point. But talk about something that has not even a whiff of experimental evidence. String theory is in that category.
Yeah.
But
That's just not a theory at all.
I think that any theory of quantum gravity is going to get you around infinite mass anyway. And at this point, we don't have strong evidence for any of them. I don't want to say that string theory is not science. It's an extrapolation from our best science, but is it a very deep extrapolation? So the hope was that here's a theory that's based on our best quantum field theories. It solves a number of problems. Before strings came along, we had great difficulty creating quantum gravity, and string theory happened to have quantum gravity for free. It was built in. It was like, wow, this is wonderful. What if in a few years we can solve this? There's only one answer, and if there's only one possible theory of everything, and this is it, we're done. We can skip all that experimental stuff. But unfortunately, that wasn't true. There are lots of string theories, and we can't make predictions from them. So it was a good direction to explore, but so far it hasn't really paid off.
Yeah, I remember in about 1983 or 84, physicists telling me that, yeah, string theory was going to have everything solved in 10 years. That was a while ago.
Yep.
I'm still waiting for one of them to tell me what to build to test it.
So apparently the person on YouTube has been asking the questions about finance and whatnot, is continuing to talk some more about finance as a problem. And the only thing I can think of specifically where finance goes off the rails significantly is the free market ideology. So free markets in terms of goods and services has proved itself to be immensely valuable to helping elevate the standard of living and the quality of life for people all over the world. And free markets involve things like comparative advantage and competitive advantage. Comparative advantage is I can mow the lawn well, but I it's better for me to pay a 13-year-old to mow the lawn and spend my time writing or doing science talks rather than having my time invested in mowing the lawn, for example. Now I happen to mow the lawn also, but that's a qualitative or a concrete example of something called comparative advantage, where you may do one thing really well, so you should spend your time doing that thing rather than other things that you can do less well. So there's lots of ideas about comparative advantage and competitive advantage that are entailed in economic principles, especially including the principle of free markets and free trade. All right. Why does that have to do with finance? Well, one of the big problems is that starting about in the 1990s, with some of the rules that were changed in the United States regarding finance, the national governments and national financial institutions and banking institutions started treating finance transactions like currency transactions, exchanging rubles for dollars and exchanging Deutschmarks for euros, etc. I guess that was about the time that Deutschmarks went away. Anyway, if you apply these same principles of free and open markets that are applied to goods and services, and you apply those to finance, then it leads to some really problematic outcomes and can actually be very significantly harmful to things like developing economies. It leads to speculative bubbles in currencies and sovereign states and all kinds of stuff. So I don't know if that's what our speaker on YouTube was talking about, but it certainly reminded me of the issue that applying some of our naive assumptions about the way the world works, even sociologically and economically, to a different context might lead us into dangerous realms.
Okay, I'm going to jump in for a moment here, getting back to sort of the original question about finance and optimism and things like that. And we were originally talking about sort of positive thinking essentially being good for the brain and the mood. But that does not mean that you have to act on every idea that you think is cool because you're in a good mood. And when you start dealing, and actually I'm going to back up and say one of the interesting things also in physiology is the basic concept of homeostasis, which basically means that the body likes to be on an even keel, more or less. And it tries to sort of revert to an even keel. And that is done by way of what are called negative feedback cycles, which are regulatory cycles. You don't wind up getting too much of anything or too little of anything. Positive feedback cycles are rare in physiology because, as I said, generally speaking, health is involved with homeostasis. Positive feedback cycles are amplifying cycles. It's how amplifiers work, in fact, as opposed to a thermostat, which is a good example of a negative feedback cycle. You want a constant temperature, you get a negative feedback cycle with a thermostat. But when you start dealing with positive feedback cycles in the stock market, then you start getting all kinds of bad things happening. This accounts for the tulip mania in Holland, the dot-com boom, the real estate crisis in 2008. A lot of these speculative booms are basically things are going up, prices are going up, so people buy in, which drives the price up, which drives the price up, and it's completely detached from reality, and eventually the bubble is going to burst. And that is a case of, well, irrational optimism or irrational exuberance, as it was termed.
Right.
And, that doesn't really have to do with physiological systems. And just because you're in a good mood and generally optimistic does not mean that you should divorce your thinking from reality. And that is where finance often gets us into trouble, is because finance people can sometimes be very optimistic, But the problem is that then for a while, the numbers support it. As I said, if prices go up, people buy in, and prices go up and people buy in, and so on. You wind up with a positive feedback cycle, and positive feedback cycles almost by definition cannot be sustained.
Yeah, right. I'm reminded, maybe next time we'll start on a topic of the logistic curve. It's one of my favorite topics in the general education about science, is the logistics curve versus the exponential curve, and what that means for real systems, including biological systems and economic ones. So again, let's go ahead and wrap up. People probably have other things to do with their afternoons and evenings. And once again, a heartfelt thank you to our panelists. We'll see you again in 2 weeks.
Bye again.
Good weekend.
Bye.
Have a wonderful day.
Yeah, have a great rest of your day and a great weekend. Bye.